we're starting a new extension 1 topic called combinatorics. Okay, this is a list of exercises to complete. The exercises that begin with 6 point something are from your new senior textbook. The exercises that begin with 14 something are from Cambridge, and the ones from Cambridge I've just kind of selected to kind of extend your understanding a bit. They've got some interesting, tougher problems or different problems to the new senior textbook. So work your way through, tick them off when you've done them. In this video we're going to have a look at the fundamental counting principle and factorial notation. Okay, at the beginning of each section I've put the syllabus dot points we're covering. Make sure after we finish the section you read through and check you understand how to do the syllabus dot points. Okay, let's start. So the fundamental counting principle, or in other words the multiplication principle. This is what it says. If a selection can be made in R different ways and a second selection in S different ways, the two selections, one after the other, can be made in R times S different ways. Okay, now that's 2 stages, but it can be extended to any number of stages, not just 2 stages. So here's an example. Imagine I've got 3 cards labelled 1, 2, 3 in a hat, and I've got 2 cards labelled X and Y in a second hat. How many selections are possible if a card is drawn from each hat? Well, I could have drawn a 1 first, in which case my second could be an X or a Y. I could have drawn a 2 first, in which my second would be an X or a Y. Or I could have drawn a 3 first, in which my second would be an X or a Y. So hopefully you can see that from this list of the sample space, there are 6 options. Okay. Now, the easy way of thinking about it is you've got 3 groups of 2. Okay. So one technique that we're going to be using a lot in this particular chapter is drawing little dashes to help us visualize what's going on. So the first dash would be the first hat, the second dash would be the second hat. How many options are there for the first hat? Well, there's 3 options for the first hat. How many options for the second? X and Y, there are 2. You do 3 times 2, which is 6. Okay, so that's using the multiplication principle. Okay, that was a fairly easy example. Let's have a look at some more. Okay, so we're going to have a look at examples with replacement. So as each stage is completed, the total number of objects remains the same because you keep replacing. So here's an example. How many 8-digit phone numbers are possible? So phone number, we're not restricted by area code here. We're just told the only restriction is 8-digit. So I've done 8 little dashes here. And each of those dashes are going to be filled with the numbers 0 to 9, which is 10 options. So 10 times 10 times 10, 8 times, or just 10 to the 8, right? So that's the answer for A. For B, how many 8-digit start with the prefix 9665? So 9665. Now, those are fixed. There's only one way of doing them. It has to be a 9, has to be a 6 in that place, 6 and a 5 in the last place there, the 4th place, sorry. And then we've got 4 places left, and each of them, there are 10 options. So it's going to be 10 to the power of 4, nice and easy. Okay, one thing I forgot to mention is while I'm working through the video, feel free to pause and copy your own notes. Hopefully you've printed them. How many 3-digit numbers are there? So it's 1, 2, 3. Now, for a 3-digit number, remember that we can't start with 0. Okay, this is not a 3-digit number, it's a 2-digit number, 23. Okay, you can't start with 0. So this first position is only 1 to 9, so there's 9 options, but all the other positions here, second position and third position, can have 10. So when you do that, you get 900 3-digit numbers. Okay, Next one. How many number plates for cars? We've got 2 letters of the alphabet followed by 3 digits. So it's 2 letters, letter, and then we've got 3 digits, 0 to 9. Okay, there are 26 letters in the alphabet, so that's 26, and there are 10 digits from 0 to 9. So it's going to be 26 to the power of 2 times 10 to the power of 3, which is 676,000. So how many of these have both letters the same and all 3 digits the same? So let's have a think. So for my first letter, I've got 26 options. I can pick any of the 26, but no matter what I've picked at the beginning, the second letter has to follow suit. So there's only one option for the second letter after I pick the first. Now for the digits, for my first digit, I've got a choice of 10 different digits, but then the other digits must follow suit. So if I picked, say, a 6 first, this would have to be a 6 and that would have to be a 6. So they've only got one option there. So you end up getting 26 times 10, 260 options. So everything we've done so far has been with replacement. Now we're going to have a look at examples without replacement. So as each stage is completed, the number of objects decreases by 1. We lose an object each time. So how many ways? We've got a class of 16. We want to select the president, a vice president, a treasurer, and a secretary. So 1, 2, 3, 4 positions there. President, vice president, treasurer, secretary. Okay, there's 16 options for the first, but then I've used that one up. So the next will be 15, and then 14, and then 13. Okay, and that's 43,680. Now for question 3 above, this is the number plate question. How many plates are possible using both letters the same and all 3 digits different? So the letters have to be the same, so letter, that's going to be 26 for the first, and then the second one is fixed. But then the digits, they have to, all 3 of them be different. So I've got 10 options for the first digit, 0 through 9. Okay, and then the second digit I've got 1 less, so it'll be 8. And then the third digit I'll have 1 less again because I can't repeat. So it'll be 8 there for the last digit there. So you can see 10, 9, 8 there for the digits because I'm not allowed to repeat. They've got to be different to one another. Okay, so putting that on my calculator, I got 18720. Next one. In how many ways can 5 people form a straight line queue at a bus stop? So I've got 5 people forming a queue. It's assumed that everyone has to be part of the queue. Okay, it might not be entirely clear, but everyone has to be part of the queue. So there's 5 spots here. First in the queue, there's 5 different options. Second in the queue, there'll be 4. Then I've used that person up, so there'll be 3 next, then 2, then 1. Okay, put that in my calculator, I get 520. All right, now we're going to be decreasing like this a lot, starting with a number and decreasing by 1 and going all the way to multiplying by 1 a lot. And we're going to be doing it so frequently, we're going to introduce a new notation to describe that. We call that factorial notation. So the product in the previous example can be written neatly as 5 with an exclamation mark next door, and that exclamation mark we call factorial. So 5 factorial means 5 times 4 times 3 times 2 times 1, which is 120. So informally, anything factorial is that number decreasing by 1 till you get to 1. So n factorial is the product of all positive whole numbers from n down to 1. Okay, and in general, the number of ways to arrange n different objects in an ordered list is given by n factorial. Okay, so this is describing if I've got 5 people in a queue, all of them are in a queue, and we want to know how many ordered arrangements can we make with those 5 people. It's going to be 5 factorial. Okay, if I had a queue, 6 people, how many arrangements? It would be 6 factorial. Okay, so there's n people. I want to arrange them in n different ways. that can be done by n factorial. Now there's a factorial button on your calculator. It's like the top right of your calculator. So if you want to do 2 factorial, you just do 2 and then you hit the factorial button. Okay, so that's 2 times 1. It'll be 2. I can work some of these easy ones out in my head. 3 factorial, 3 times 2 times 1. We multiply all the way down to 1. That'll be 6. 4 factorial, we start from 4 and we go down 1 at a time till we hit 1. It's going to be 12 times 2, 24. And 10 factorial, no way I'm doing that in my head. But that'd be 10 times 9 times 8, all the way down to times 1. In my calculator, 3628800. So that answer there, 10 factorial, that would be the amount of arrangements of 10 people forming a queue. Okay, which is just over 3.6 million. All right, what I would like you to do, work on 6.1 from the new senior textbook, questions 1 to 12. See you in the next video.